I'm Steve Cauffman, studying under Dr. Gillen at NC State, and today I'm going to talk to you about investigating spatial performance following perspective change. So I'm just going to go through some introduction background research about spatial transformations and using aerial and ground views, and talk about the study hypotheses, the method, the results, and the discussion. So to start, some background, unmanned aerial systems, or UASs, are becoming much more prevalent in society and civilian use outside of military context, such as emergency response, law enforcement. And market projections in 2013 were predicting that there would be about 160,000 units sold by 2023. And so because of this increasing prevalence of these in just our everyday life, it's important to understand human performance on tasks involving these tools. One issue that comes up anytime you're interacting with a drone or a robot that perceives the environment that presents it to you on a screen is remote perception. And David Woods talked about this a lot in a paper with titled Rosler and Woods. And basically what happens when you use an unmanned aerial system is that you have to perceive the environment through the camera that is connected to them. And this disconnect between sensation and perception can create errors in human performance. One example of this was that operators during 9/11 rescue operations experienced navigation difficulty because they had a hard time interpreting the spaces that they were trying to navigate the robots through, and so there were spaces that they wouldn't fit, and they weren't able to tell very easily. And so unmanned aerial systems offer this new aerial view of the scene that's not quite as high as a helicopter, and it's higher than the ground view that we normally get. And so they allow us to perceive true depth of the scene, whereas ground views that we normally get tend to be compressed and don't offer us good ideas of the depth of objects. And so there's a conduit of integration that is required on the part of the human to take this aerial view and combine it with their ground view to get a better sense of the environment. And when humans interpret objects in the environment, we develop a spatial reference system. So we imagine the environment in like a 3D orthogonal axes, and we kind of interpret objects based on these axes in the environment. In studies done on this, participants in navigation trials, there's an encoding specificity that happens. So if you learned a route from the aerial view or the ground view of the route, you would perform better when you were asked to navigate from the same perspective. They also showed that to be recognized image was consistent with an encoded perspective, so performance was better. When we do spatial transformations, we tend to use two types of cues. There's object-based cues, which is where are the objects in relation to each other. And then there are egocentric cues, so where are the objects in relation to us. And when we move through the environment, we have to constantly update these two types of cues. And when we have to update these cues, they become disrupted and disorientation occurs. This was shown in a paper by Wang and Spelke in 2000. They had participants sit in a room, and they learned a set of objects in the room from a perspective, and then they rotated the participant, and they showed performance decrements in pointing error of the participants. So the current study seeks to explore perspective change in a task that's representative of UAS use. So hypothesis one was that congruent perspectives in trials will result in faster response times and less error than non-congruent perspectives. And then hypothesis two was that transitions between an aerial view to a ground view will result in less error than the reverse because the aerial view is providing the increased depth cues that would result. So the method for this study, there were 4 types of image pairs. There was aerial to aerial, aerial to ground to aerial, and ground to ground. There was 2 levels of object density, so there were 3 or 5 objects in the scenes. And then there were 2 levels of stimulus presentation duration, so they would either see the stimulus slide for 5 seconds or they would see it for 10 seconds. This was a completely within subjects design. So we used 18 participants from the North Carolina State undergraduate research pool, 10 males and 8 females. And our 2 measures for the study were response time and error. And error was calculated using the Euclidean distance formula, which is as you probably might know, is the square root of x1 minus y1 squared plus x2 minus y2 squared. And so the task was sets of objects were presented from an aerial or ground view in a stimulus slide, and each aerial view was taken directly above the ground view with a downward viewing angle of 60 degrees. And stimulus presentation duration was set to either 5 or 10 seconds, and this was randomized trial to trial. So this is an example of a trial of an aerial to ground transition. So the slide on the left is the stimulus slide from an aerial view, and you see the three objects, the pink blocks that are there. And in the response slide in the ground view, one of the objects was removed, and the participant was asked to click what I thought the missing object was. And the error was calculated as the mouse click XY coordinates on the screen to the center point of the block. And so for each trial, participants received the stimulus slide for 5 or 10 seconds, and then a distractor cross was presented for 3 seconds. And then the response slide is presented with one object removed, and the participants click where they think the missing object is supposed to be. And so the results for this showed that response time was slower in non-congruent trials compared with congruent trials. That is consistent with the literature. And it was slower for when there was a higher number of objects present, so higher load on working memory. There's also a significant four-way interaction between the stimulus, response, stimulus duration, and the number of objects. And I will show that in a graph here. So this graph is a big one, so I split it in half. And for this half, this is for 3 objects in the scene. On the y-axis is the mean response time, and on the x-axis is the stimulus duration, so 5 or 10 seconds. And as you can see, the top 2 lines are the congruent trial or the non-congruent trials. So the response times were higher than non-congruent trials, so when they were transitioning from aerial to ground or ground to aerial, compared with the congruent trials where they were going from aerial to aerial or ground to ground. And then the second half with 5 objects, same effect. There was an increase in response times for the non-congruent trials. There was also an increase in response times between the stimulus duration, presentation duration, and not really any significant differences in the congruent trials. For error was significantly higher for the aerial to ground transitions than the other trials. And then there's a significant main effect for error on object density. I'll show you a graph of the trial types here. So in this bar graph, the y-axis is standardized screen units. The experiment administration software that was used for this study that calculates the XY coordinates based on a normalized screen unit distance. So 0, the origin point is the center of the screen, and then 1 is the very edge of the screen. And so in this graph, the aerial to ground image pairs resulted in the highest amount of error. The ground aerial and ground ground transitions resulted in the same error and less error than the aerial to ground, and aerial to aerial resulted in the least amount of error. So with these results, there's partial support for hypothesis 1. Ground to aerial was not significantly different than ground to ground, which is contrary to prior research. It should have been less error according to the prior research in the congruent trials. And hypothesis 2 was not supported. Aerial to ground trials showed the highest amount of error. And that might be because when you are presented with an aerial view first, you receive a large amount of context about where the objects are in relation to each other. And when you're presented with that ground image second, it removes the context from that aerial view, and you're all of a sudden left without any information. So the applications of this study, prevalence of UAS requires exploration of how they affect human spatial judgments, and understanding how these errors arise in human perception can inform the design and training for these systems. And this paradigm offers an efficient way to add in manipulations for further study. And so future directions can include the use of landmarks. This is already done in a study that is currently being prepared for publication. And also complex perspective rotations. Another study that's in preparation right now is going to include rotations along vertical and horizontal axes to add in complex rotations around a conceptual dome around the scene. Some limitations of this study are we used a low fidelity environment. We use Minecraft because it was easy to download a virtual city and develop the images that way. And there were no assessments of spatial abilities or video game experience included in this study, but they were in follow-ups. And we also use static images here instead of videos. Videos might have kind of increased the ecological validity of this. And so, special thanks to LabMates, help and support, Dr. Gill, obviously, who's a co-author on this. Yeah. any questions.
That's a pretty nice and short talk, and so we have a few more minutes for questions. Yes?
You're responding on the ground, people see an image based on the ground robot's perspective, and then they click on where they think the object of interest is, right?
It's based more on the incident commander, based on the National Incident Management Framework, standing on the ground. That usually in rescue operation procedures, the incident commander will walk around and do a scan of the environment.
So for the recording of the error measure that you're using?
Oh, for the Euclidean distance?
Yeah. How do they, so it's literally clicking on the screen is how that's recorded?
Yeah, so the mouse click.
View, if you will, right, and making a mark on that screen.
Yes.
Worry at all about the distortion of the view as, like parallax kind of problems where things in the distance are going to take up a very small amount of 2D screen real estate, so your error in space could be very large for objects that are very far away from the perspective.
We did not include that, but that could be useful for future studies. This was simply recording the XY coordinates of the mouse click versus the center point of the object, or where the missing object was supposed to be.
I have a question. Have you considered measuring the mental rotation, and how does that relate to this?
We did not in this one, but we are going to include mental rotation measures. We did for the follow-up with landmarks, and we're going to include mental rotation in the